Okay, ladies and gentlemen, welcome back to graphing rational functions. This is Resh Mahaber coming to you again from Wayne State University. The first thing we're going to need to talk about is a quick review of just graphing normal polynomials. And we're not talking about the guys that we know are good-looking functions, meaning x squared, x cubed, square roots, the guys that we know we have a structure to. We're talking about guys that could look any old way. So I'm going to bring you back to home base. So let's say I had to graph this guy, which was x squared, x plus 3 cubed, and then x minus 2, right? So what do you need to look at here? Well, two things is really simple, okay? You just need to figure out, oops, sorry there. We need to figure out what the intercepts are. And then finally, make a sign chart to figure out when this function is positive and negative. So then make a sign chart. Now, if you looked at video, which was on graphing polynomials, I would encourage you to look at that because that's really going to be where we get the maximum amount of information for how we graph rationals. It's the exact same thing, except we have to worry about two things, which are, well, one thing, which is asymptotes, which is going to be the new addition. So I'm going to try to do these both at the same. I'm going to do this problem here, and then hopefully it'll give us a little bit of intuition of how the other ones kind of work. So there are two types of intercepts, x and y intercepts, obviously. So for an x-intercept, which, by the way, if you looked at the video again, actually, as a matter of fact, don't watch this video until you've seen the other one. That would probably be the best way to do it. So you want to look at the video for graphing polynomials, just in general. Okay, so here we go. It's section 3.2 if you guys are wondering. So let's look at what our x-intercepts are. Well, that's if you have 0 in for y, what are the possible solutions? Well, from this factor, you're going to get a root of 0. For this factor, you're going to get a root of -3. And for this factor, you'll get a root of 2. Very simple. Y-intercept. This means you're plugging in 0 for x, and you got to gang out of the y. So how are we going to do that? Well, plug in 0 for x. Well, this one alone, I really don't need to know what's going on here because this is going to be 0, and 0 squared is 0 times anything is also 0. Easy peasy lemon squeezy. Now, note, here's something that's cool. How do we find the sign chart? We look for zeros and we look for bad guys. But because there's no denominator here, right, we know that there's not going to be any bad guys. So what are the zeros going to be? When you set the function equal to 0. But isn't that what we did to find our x-intercept? So I already know that my zeros are going to be this guy, and this guy, because I set my functions equal to 0. And these are the solutions that I came up with. So literally, your x-intercepts are your zeros. And that is the big piece of the puzzle that you would learn if you watch video 3.2, which once again, you should have watched before you watched this one. So zeros are really x-intercepts. That is very, very important. So let's make our sign chart. So here we go. Once again, guys, I'm going to try to keep the video under 20 minutes, but I feel this one might be a tad bit longer, so stick with it. All right. So now this is the big key behind doing these graphs is this key called multiplicities. And I'm going to write this in my little think bubble. Multiplicities is this idea of duplicate roots. Now, what is the benefit behind it is that it tells you the shape of the root that you're dealing with when we graph it, and also it tells us how the sign chart looks. So what do we know? We know that if we have a multiplicity, all it means is that we have a duplicate. Okay? So I want you to think about this. I swear I can spell. There we go, duplicate. So if you look at the root at -3, what's the factor that created it? It's this one. Well, if you have it cubed, that means you have 3 of the same guy. So the multiplicity on this is 3. Excuse me. 0 came from this factor of just x, and it's squared. So therefore, the multiplicity is 2. And this 2 came from x minus 2. The multiplicity on that is 1. It's all by itself. All right. So it seems like we're ready to rock and roll. So this is kind of the idea. If you have a even multiplicity, my spelling's off today, then the sign chart will alternate. Oh, sorry, not alternate. I'm just all backwards today. The sign chart will stay the same. Okay, it won't alternate. But if it's an odd multiplicity, then it'll alternate. So what does this mean? Let's say we found out the sign of one of these. Pick one randomly. Okay, so you plug a number in here and let's say you get plus. Because I know this one's odd, then these two should alternate. And because, now also because this is positive, and I know this one's even, these two should stay the same. And because I know this one's odd and this one's positive, then this one should alternate. So you see how it kind of works. So what's the big point here? If you screw up that first one you choose, everything else is going to be wrong. So you got to make sure that is 100% on par. So how do we figure it out? Well, you got to pick a number and plug it in. Okay, so I'm going to pick 1 because that seems like the cleanest one to plug in. 1 squared is 1. 1 plus 4 is 1 plus 3 is 4. Cubed is a big positive number. 1 minus 2 makes it a negative 1. Negative 1 times 2 positives ends up giving me a negative. So that means this is negative. See, if you screwed it up, I'll screw up everything else. So here we go. If it's odd and this is negative, then it should alternate. If this is negative, this is even, should stay the same. If it's odd and it's negative, it should alternate. Done, done, and done. All right, I know we haven't even gotten to actual graphing of this, of rationals yet, but we'll get there soon. We'll get there soon. So here we go. Here's our graph. So first things first, we need to draw our x-axis and our y-axis. That is a terrible looking y-axis. Y-axis. Okay. Now, here's something that's also very important about the multiplicities. So I'm going to put points where I think my zeros are. And once again, whatever is in are my intercepts also need to be on here. So 0, 0 should be 1, negative 3, 0, and then 2, 0. All right. Now, here's something. So that's all the intercepts. So let's move to our sign chart and figure out how this thing looks. The multiplicities determine the shape of the roots. Okay, the shape of the roots is once again came from graphing. Well, because this is multiplicity 3, what do degree 3s look like? They look like this, or they look like this. So how do you decide which way it looks? Well, it's positive, meaning that it's above, and then it's going to be hit the 0, and then it's going to be below. These are zeros. Maybe I should leave it then. Then it's going to be below. Okay, that looks pretty bad. Then it's going to be below. Okay, very simple. Now for this guy, he is below on the left of the 0 and below again. But why does that make sense? He's degree 2. What do degree 2s look like? Quadratics. That means it's like a little parabola. So it should look something like this. And then finally, it's below and then above. And because it's degree 1, it should be a straight line. So notice that degree 1s and degree 3s are both odd. They alternate. But because he's a third degree multiplicity, he's going to look different around the roots. Now everything else is kind of variable. This is where you kind of get to connect your dots and however you see fit. So it can look a plethora of different ways. So that means I don't know if this goes really low or kind of low. Okay, you'll know when you hit calculus. Same thing here. I don't know if this is going to go here or if it's going to do some stuff like that. I don't know if this is going to do this or this or this. Okay, so this is what I'm going to do. I'm going to make this up as I go. Here we go. Make that look a little different and make that look up. Now you'll know exactly how this thing looks when you get to Calc 1, because then you'll be able to determine inflection points and relative max and relative min. So knowing what a derivative is a huge piece of the puzzle. But right now, all we're really concerned with is, can you give me the shape of the roots and what this other and what the zeros are, and actually make the sign chart, follow the process. So we just spent 10 minutes talking about this in this peer review, because to do a guide that looks like this requires the same process. So let me go ahead, switch colors, and here we go. Something happened. Okay, we're still there. Okay, good deal. So what does it look like? Well, here we go. Oops. Let's say we wanted to graph f of x, but this time I want a rational guy. So I'm going to make the numerator this, and then this, same kind of deal, and I'm going to do this. Okay? And now down here, I'm going to make this guy x to the 4th times x plus 2. squared. All right, so it looks fairly simple. Now note, if this thing is factored, your life has gotten much better. If it's not factored, then your life sucks, because then you have to factor it out to actually be able to do all this good stuff. So if it's multiplied out, and you end up getting x to the 6 on top, x to the 6 on bottom, and some stuff, then you got to work. You got to do some work here, major work. Okay, so that's why I'll recommend you look at video 3 on factoring large polynomials, because then that'll help immensely. All right, so there's only a couple things you need. Okay, and it's just like before. You need to figure out what the intercepts are. And then you need to figure out what and what I'll do is I'll work this example a couple different ways by changing the problem. I feel like that's more applicable for the situation. And then you need the sign chart. You'll notice I kind of left 2 out. What goes here? Oh, well, this is what's called asymptotes. Now, asymptotes, you have 2 types. Vertical asymptotes and horizontal asymptotes. Now, vertical asymptotes are the guys that make your denominators equal to 0. And we can't stand these guys. These are guys that would break our machines, right? So like in our domain restrictions, if we had -2, that'd make our denominator 0, and we can't divide by 0. So x equals 0 is a guy we don't like, and x equals -2 is a guy we don't like. Makes good sense, right? So at these things, we're going to have what's called a vertical asymptote, or a vertical line there. And good news is vertical lines have the equation of x equals a number. So it'll be like a dotted line at x equals 0. Don't worry, I'll go through and we'll fill in the blanks. Horizontal asymptotes are the other guy that's the other pain in the butt. Okay, we'll go back and we'll find the intercepts in the sign chart, but I figured this is the time to talk about it. What do I mean by pain in the butt? Because you have to make a decision, okay? You have to determine what so the first thing you got to do is figure out what the degree of the numerator is. I'll make numerator, I'll abbreviate it as num, okay? And what the degree of the denominator is. And then you have to compare the two. The dinosaur. Okay, now what do I mean by degree? If I were to multiply this out, this would be x squared stuff times x cubed stuff at the most times another x. So it's going to be x to the 6 plus stuff, right? And this guy will be the same thing. X to the 4th, this would be x squared stuff, so x to the 6th stuff. It's important you know what degree it is, and now I'll go into the reason why. Well, this is the reason why. Because this is the case. If the degree of the numerator is equal to the degree of the denominator, then what you do is you look at the ratio of the coefficients of the degrees, of the highest degree. So you look at this. So your horizontal asymptote, which is a dotted line that shows tendency, will be at y equals 1 over 1, which is just that, right? So you have a horizontal line at a y equals 1. I'll graph this and I'll show you. Okay, so for this particular example, we have that. Now, don't worry, you can only have one of these three. So for this particular example, we have this. But let's say they weren't the same. Let's say the degree of the top, yeah, top is better than bottom, right? Top is less than the degree of the bottom. Then what does that mean? Well, that means that the top is growing less than the bottom is. So eventually, if we go off for far enough right or far enough left on the graph, the numbers will be so big that the bottom will be so huge that the numerator will be insignificantly small, meaning that it should bottom out back at the origin, or y equals 0. And then finally, if the degree of the top, last kind of one, is if it's greater than the degree of the bottom. Then what happens? There's no horizontal asymptote. And I know some people learned about slant asymptotes, right? Which is okay, but right now we're just interested in a horizontal asymptote for these particular problems. Okay, so bottom line is, this is where we're at. So we know we have a horizontal asymptote here and vertical asymptotes here. So I can already tell you, I tend to draw my graphs after I have all my information, but I'll draw this on the graph so you actually see what I'm talking about, and then I'll erase it. So that means that at 0, I have a horizontal asymptote, a vertical asymptote at x equals 0 from this, at x equals -2 from this. Oh my goodness, that is a very bent vertical asymptote. I did it again. And then here I have a horizontal asymptote at y equals 1. Now you cannot cross your vertical asymptotes. Okay, you cannot cross them. But you can cross a horizontal asymptote inside the graph. Horizontal asymptotes really just determine your end behaviors, meaning that as you go off far enough left and far enough right, these are like your lines that it bottoms out at and bottoms out at. Okay, so it's like a settling point. But in here, it can be doing a whole bunch of weird stuff, but here, when it gets out here, it should smooth out down. Okay, so this is kind of what's going to happen. Alrighty. So now let's figure out the rest of the stuff, because we still need to figure this out. So I'll come back and I'll reiterate the graph later. Usually I find all this first before I even touch this, but I wanted to really stress the differences, because the intercepts are the exact same way we did it for the rational polynomial. So here we go. Intercepts. Well, once again, for my x-intercepts, I need to make y 0. Well, if you make y 0, the only thing that's going to make it 0 is if, I think I made a boo-boo, guys. Let's change this to x minus 1. Yeah, that'll make it a cleaner problem. X minus 1. So that means your vertical asymptote will be that, and nothing else changes. All right, fine. So then your x-intercepts, so if you make your y equal to 0, you'd clear your fraction, and it'll leave you this thing on top, which will still give you 0, 0. It'll give you negative 3, comma 0, and make this 2, 0. Yeah, people are probably saying to themselves, well, why did he change this to x minus 1? Because this would simplify. I don't want that to happen. All right, so x-intercepts, y-intercepts. Make x 0, what's y? Well, still 0 across the board, right? 0 times all this would be 0. Divided by something that's not 0 still would be 0. All right. Remember, these are the same as zeros that go on your sign chart, right? So here we go. So what goes on sign charts? Zeros and bad guys. So here's my zeros, negative 3, 0, and 2. Well, what are bad guys? Bad guys are the guys that make this thing equal to 0, because we don't want the denominator to be 0. I want to throw them out. Check this out. We did that for the vertical asymptote. So really, key word here, vertical asymptotes are really your bad guys. So this is going to be where negative 2 would be, and then this will be what 1 would be. And label your stuff. This is a 0, this is a bad guy, or a vertical asymptote. This is a 0, this is a bad guy, and this is a 0. Okay? As a matter of fact, I've decided that I'm going to erase this graph, and then we'll talk about it in bigger detail. I'll draw everything from scratch. Okay? So now what do we need to do? Well, it's the same thing as last time. What did we do last time? After we figured out zeros, right, we need to determine the multiplicities. Well, let's determine the multiplicities here. What's the multiplicities? Well, you have to look at the factored form, right, to see what the multiplicities are going to be. On x squared, which is that had this factor, multiplicity was 2. So on 0, the multiplicity is 2. At x minus 3, that came from this factor, multiplicity was 3. I did it again, guys, sorry. I'm still learning how to use a computer. It's really weird, right? So this is a 3. Okay? It was a 3. At x minus 2, the multiplicity is 1, and that produced our 0, that's a 2. So that's this guy. Now, x minus 1, the multiplicity is 4. Which means, what was this? This was a bad guy that it contributed to this. So at this bad number, this vertical asymptote, it's multiplicity 4. And then finally, this guy has multiplicity 2. Alright, so this is the fun part. Here we go. We just need 1. Remember, even multiplicity stays the same. Odd multiplicity alternates. Right? So I don't want to plug in any fractions. At least I'll have to plug in some fractions here. Maybe I'll plug in negative 1 for right here. Remember, I just need 1 to break it loose. So let's see if I can do some math here. Negative 1 squared is positive. I did it again. Goodness, guys, I'm sorry. Negative 1 squared is positive. Negative 1 plus 3 cubed is still positive. Negative 1 minus 2 is negative. Negative 1 minus 1 to the 4th is positive. Negative 1 plus 2 squared, that's positive. So we have positive times a positive times a negative is negative up top. Positive times a positive is a positive on the bottom. That means this is negative. All right, guys, so here we go. This should all flush out our sign chart super duper quick. If this is negative, then because it's an even multiplicity, this should be negative. If this is negative and this is an even multiplicity, this should be negative, right? Because they stay the same. If this is negative, odd multiplicity should finally alternate. Let's go backwards. Negative, even, stays the same. Negative, odd, turns around. All right, so far so good. So far so good. All right, now here's the key piece to all this. Anything that's on number 1 and number 2 needs to be on my sign chart. Needs to be on my graph. So let's see if I can graph this without making any boo-boos. It's a small graph, guys. Here we go. 0, 0 is my 0. Negative 3 is my 0. 2 is my 0. Y-intercept, also in the exact same place. Life is good. If the vertical asymptote's at 1, right? At negative 2, there's another vertical asymptote. Okay? At y equals 1, there's a horizontal asymptote. So it should be just on the end behaviors, remember, not the entire graph. Okay, because that's where it should bottom out to. All right, so here we go. This is where things get fun. I'm going to draw everything I know for sure in red, and then I'll clean up the rest on the end. So I have a 0. It's degree 3, positive, negative. So I should do the same thing. Right? Same thing as before. A 0 at, so I just put in my vertical asymptotes. Let's take care of my zeros. This should be quadratic-like. Degree 2. This guy is below and above. Should be a straight line. That's my best straight line I got. All right, guys. So now let's connect the dots. To the left of negative 3, it's positive, which means above the x-axis. But this describes end behavior. So that means as you get further and further away, it should bottom out to this line somehow. Now, I don't know if it does this, or if it does this, or if it does this. This is all variable. Okay, you'll learn more about that in calculus. I have big pause today, and everything's moving on the screen. So I'm just going to settle on that one. Okay. Now, finally, what's happening here? Well, from negative 3 to 2, it's negative, but it's a vertical asymptote. That means I can't come back above the y-axis. So what's going to happen here is all these numbers are going to get used. Well, how close do I need to get? As close as possible, because I'm trying to say that all the numbers from negative 3 to 2 are getting used. So it's going to hug the line as much as possible. Now, where do I pick up at? I could pick up here closer to the asymptote, or further away, because it's kind of the same concept. All of your asymptotes, all the asymptotic behavior for vertical asymptotes, it should be hugging lines. So it's going to hug the vertical asymptote. At negative 2, where's it going to come from? Well, this negative lets me know that it's going to come from below, and it should come up. Remember, it's not going to cut the vertical asymptote. It's going to push there. But I could cut a horizontal asymptote. Notice I bottomed out further out, but I went right through it there. Vertical asymptotes cannot cut. They're bad numbers. Okay? Now, the left of 0, 0 is right there, and needs to be negative. So it's going to do the same thing. It's going to hug the asymptote. And then finally, at 4, it's going to be below. So it'll hug the asymptote, you hit the root. And then finally, when we get to 2, it should be positive, which means above the x-axis. So the question is what happens? It could do the same thing as it did over here, or it could do something like this. I'm going to choose for it to do something like that. Really stinking easy, guys. Really, really stinking easy. Okay? It's really attention to detail and detail-oriented. Now I'm going to change this a little bit, just so you can kind of get a feel for what would happen. Okay, watch this. What if I did this to this? Instead of making it a 3, I made it a 2. That means what? This wouldn't change. That wouldn't change. That wouldn't change. And this wouldn't change. The math would be the exact same. The vertical asymptotes would not change, right? Because the denominators are still the same. But check this out. What's going to change? The horizontal asymptote Is the degree of the numerator equal to the degree of the denominator like before? No. When you multiply this out, it's going to be degree 5. Right? And if it's degree 5, it no longer applies to this. It's less than, so it's going to be y equals 0. Okay? Which means, now what? Well, let's look at our sign chart now. This means that what's changed? The root that gave us 0, it won't change. The only one that'll change is this. That means it's a multiplicity change. So negative 3 now would be a 2 multiplicity. Which means this guy that was negative, this will stay the same, that'll stay the same, that'll stay the same, that'll stay the same. But instead of this being a negative 3, because it's even multiplicity, that would make this a negative. So how does this change the entire graph? Well, everybody watch the birdie now. Your horizontal asymptote's at y equals 0. This is the first piece of info that changed, right? And then this thing is negative. So instead of it looking degree 3 like, it should look degree 2 like. But note that now it needs to come back to the horizontal asymptote. So this guy shouldn't be this far in the air. It should be more like this. And this guy, well, shouldn't cross through. It should be right on top. So let me erase that and draw it again. Should more like this. And this guy should be more like, ugh, that looks terrible. Let me draw my root a little nicer. It should look more like this. Pretty nice, isn't it, guys? So, moral of the story is this stuff isn't hard. It's just a big attention to detail. So, I'd encourage you, no matter what you do, you keep plugging away at stuff. And here's one for you to try that I will talk about tomorrow. Okay. So I want you to graph f of x equals x squared, x plus 2 to the fifth. Why not? X plus 1 to the fifth. X minus 2 to the second power. All right, guys. So, once again, in order to go somewhere you've never been, you're going to have to do something you've never done. So, keep plugging away. And I know this video was a little bit longer than we anticipated. But as you can see, the details, it's extremely detail-oriented to just be able to go from this down to this. Now, I know a lot of it wasn't math. Most of it was just understanding what to look at to extract the information from the actual function itself to get this graph. Okay, so once again, keep plugging away, and I'll see you on the next video.